Okay, so for my example for today's lesson on the first and second derivative, I'm having a look at this problem, and it's rather than just working through the skill-based type process of actually doing the first and second derivative, I thought I'd have a look at this word investigate, which really simply, when you do your SAC, you can expect to have to investigate a problem. So this is really just about starting with the problem and then seeing where I end up and using a whole heap of information to sort of guide my decisions. There's a few hints in the question. It does tell me to use the first and the second derivative and hence sketch the graph. So we know that we're trying to sketch the graph through this investigation as well. So what I'm going to do is I'm going to use my CAS calculator, and I'm working on the iPad, so it looks a little bit different to your handheld, but I'll hopefully show you a few tricks that make it a little bit easier to do it on the calculator as well. So let's actually start by finding what the first derivative is, and we'll also find out what the second derivative is. And I'm just going to go straight onto my calculator. I can do it using the quotient rule. The first derivative isn't too bad. The second derivative gets pretty messy with some algebra, and there's some expanding and factorising and cancelling that makes it very time consuming. So I'm just going to go straight to the calculator. All right, now first trick on the calculator is, rather than actually typing out the derivative, I know I'm going to use these equations a few times. So I'm going to define the equation, and I'm going to call the first one f of x, and f of x will be equal to 2x over, what did we have? X squared plus 1. Okay, so now that's defined, I can find the first derivative by simply just using the derivative template and then put in here f of x. Okay, and I've got my first derivative. So that's negative 2 times x squared minus 1 on x squared plus 1 all squared. And you can see where the denominator there is all squared. You can see where it fits with the quotient rule. Okay, so my first derivative was minus 2 times x squared minus 1 all divided by x squared plus 1 all squared. Okay, let's go back to the calculator. Now we're probably going to need that again, so let's actually store that as something. Now I did f of x for the first derivative, so let's use, let's go define, let's call it a of x. I've just chosen a different letter, and I want it to equal that equation right there. So my first derivative is a of x now. Hit enter. Cool, so that equation's defined. So what can I do with the first derivative? Well, one of the things I can do with the first derivative is I can find the turning points. And the turning points are when the first derivative equals 0. So let's go back to my skills here, use some algebra, and solve the first derivative equal to 0. And we want to find out what x is. So when we solve the first derivative equal to 0, we get the x values of negative 1 and 1. Cool, let's write that down. So we know that the first derivative equals 0 at x equals plus or minus 1. All right, well, what does the equation equal when x was 1? So I can use my calculator here and go back, and because I've defined that equation, I can just say, okay, what is f at 1? Okay, it equals 1. So I've got when x equals 1, y equals 1. What about at negative 1? So f at negative 1. I missed my bracket there. Okay, when x equals negative 1, y equals negative 1. So not only have I got that the turning points are at x equals positive 1 and negative 1, I have that they're actually the coordinates of 1 and 1, and this will be a turning point. And we also know at -1 I got -1, so that's the coordinate -1, -1, and this will be another turning point. I don't yet know whether it's a maximum or a minimum or a point of inflection. I haven't got that far, but I have got stationary points. So let's have a look at the second derivative now. Go back to the calculator. To find the second derivative, I have to differentiate the first derivative, which we called a of x. Now I can use the second derivative function in the templates option here, but I've already defined a of x, so let's just differentiate a of x. Here we go, there's the second derivative. So it's 4x bracket x squared minus 3 all over x squared plus 1 on 3. Now I'm going to try and remember that when I go back to Notability. So 4x x squared minus 3, x squared plus 1 to the power of 3. Let's see how I go. We got 4x times x squared minus 3 divided by x squared plus 1 to the power of 3. Alright, now we can use the second derivative here to find out whether these turning points are a maximum or a minimum. If I substitute in the x value into the second derivative, if it's negative, then it will be a maximum point, and if it's positive, then it will be a minimum point. And if I substitute this x value into the second derivative, same deal. If the second derivative is negative, then that would be a maximum point, and if it's positive, then it will be a minimum point. So let's go back to the calculator. And we've got my equation there. Same thing, I want to define that. Menu, actions, define this equation. I'm just using the letters I've got down the bottom here. So let's call this one n of x. So my second derivative is n of x. If you're working this way, you've got to remember what letters you've used. And if I was in class and on a calculator, I would show you a slightly different method, but this will work for now. Okay, so let's find out when I substitute in that x value of 1 into the second derivative, I get -1. So when I substituted in 1 into the second derivative, it equaled -1. So the first derivative equaled 0. The second derivative was negative. So when I put this together in the table that we had in the textbook that I got you to copy into your notes, I find out that this is a maximum turning point. Alright, let's see what happens when we put in the negative value. So we go to my second derivative, and I now want to substitute in -1. Hit enter, and I get +1. So the second derivative is positive at -1. So the second derivative is equal to 1, or it is positive at the second part. So the first derivative equaled 0. The second derivative was positive. Put those two things together and you've got a minimum point. Alright, so if we go back to our original question and we talk about investigating using the first and second derivative, what we've found with this expression here, now this is a bit different to what we've seen before, and what we've just discovered is that it has two turning points, 1, 2, there at these coordinates, and I know the first one is a maximum and the second one is a minimum. So when I go to sketch my graph, I've already got some information that I can start putting on it. So let's just put a scale on here, call that 1, 2, 3, minus 1, minus 2. Now, sorry, just dropped my pencil. When I go to plot my graph, I know at this point it's going to have the point 1, 1. And that point is going to be a maximum. And I'm going to have the point -1, -1. And that point there is going to be a minimum. So I start to see my graph, and I might sort of make some judgments that it's going to look like this. It might look like a cubic. But we go to my original equation, and I know it wasn't a cubic. So let's just for now leave it with just those maximums and minimums shown on there. And let's keep exploring. What else does the second derivative tell us? The second derivative also tells us if the second derivative equals 0, we know that that is a point of inflection. The graph is changing from having a positive gradient to a negative gradient, or an increasing gradient to a decreasing gradient. So let's actually find out. Let's solve the second derivative equal to 0. So remember, the second derivative was n. I want to use some algebra now and solve the second derivative equal to 0. So I'm finding those points of inflection. Finding it for x, hit enter, and I've got 3 answers. I've got 0, -√3, and +√3. Now, let's also just get an approximate answer so we can visualize that. -√3 is -1.7. +√3 is +1.7. Okay. Let's come back in here. We know that the second derivative is equal to 0 at x equals 0 and positive and -√3, which is approximately equal to 0, -1.7, and 1.7. All right, what does the original graph equal at 0? Let's find that out. Go back to my calculator. What does f of 0 equal? It equals 0, so I've got the coordinate 0, 0. What does f equal at -√3? It equals -√3 on 2. All right, so it's going to be a negative value as well, so I'm still in the negative quadrant. What about when it is positive √3? It equals positive √3 on 2. So positive √3 on 2 is half of 1.7, which is roughly 0.85. Okay, so at 0 we get 0. At √3 we got √3 on 2, which is approximately 0.85. And at -√3 we got -√3 on 2, which is approximately -0.85. So if we start to put these points on my graph, I've got 0, 0. √3 is 1.7. There we go, about there. And 0.85. So 0.85 is about somewhere up there. And then the other one was -0.7, 0.85, negative, about there as well. So we start to get these points. Now this is, remember, a point of inflection. So the graph has to change from a decreasing gradient or an increasing gradient to the other one around. So here I can see, well, it's an increasing gradient. It's got to be getting steeper like that. But it has to change at that point of inflection. So I'm just going to change colours so we can see that. So it's going to kind of go across and then change the other way. So its curve changes. at this one here, it's sort of the gradient, if I'm going from left to right, has to change at that point of inflection. Didn't really get that right. Let's try that again. So, I just realised I put that dot very much in the wrong spot. That's why I'm having trouble drawing this second one. That dot's in the wrong spot. It's got to be 0.85, negative 0.85. It's going to be about there somewhere. So this one's got to go that way, and then it starts curving the other direction. Now you might have guessed by how I'm drawing this, my first step was to actually type in the equation of the graph into the calculator and have a look at the graph. So I know a little bit more, and in an exam you might have to make some of these jumps yourself. But then I've also to go through this point. So if that's a maximum, that's a minimum, and I've only got this point here, I am going to assume there's no other maximums or minimums, or they would have come up in our solutions for the first and second derivative. So it's just got to go straight through that point. And here we go. We've created our graph. So we've got a point of inflection, and another point of inflection here. And we've got our maximum, and we've got our minimum, and we got them from the first and second derivatives, and we've sketched a relatively complex graph that we haven't seen before, which is called a rational function. Now this comes up later in exercise 6G, I believe it is as well. So you do a little bit more on this later on. There you go. So we've used the first and second derivatives to investigate the function f of x equals 2x over x squared plus 1. What did we do in summary? We looked at the first derivative and solved the first derivative to find the turning points. We solved the second derivative equal to 0 to find the points of inflection, and we used the second derivative with the coordinates of the turning point to determine whether it was a maximum or a minimum. And then put all of that information together and we can create a graph. I also know for this graph, I'm just going to go a little bit further because there's some interesting information here. You can see how I've got my graph flattening out. There's two ways I can know that it's got to do that. The first one is I can solve to find the x-intercepts. So the x-intercepts we know are when y equals 0. So that's when the original f of x function equals 0. So again, using the calculator, I can solve my function f of x equal to 0. Find out what x is. Hit enter. We get only one answer. So we can't have any other x-axis intercept. So that's one way I know I can't cross that x-axis intercept. But also, if we just think about, well, what happens when my x value gets really, really large as it approaches infinity? Again, using the calculator, okay, what if it was 100? If x was 100? Now that value is a small number. All right, so we're in the hundredths now, nearly 200ths. What about if it wasn't 100 and we went to, say, what's that, 100, 1 million, 10 million? Let's get an approximate answer there. So it's 2 e to the negative 7. So that means 0.00000002. So a very small number. We're approaching 0. What we say for this graph is that as x approaches infinity, f of x approaches 0. And as x approaches negative infinity, f of x approaches, now I'm going to put a little negative 0. It's basically approaching 0, but from the negative side of the axis, because all of the values are negatives. These are what we call limits. And although they're kind of part of the specialist and methods course, they're also kind of get skipped over a lot. So if you want to do any extra research on what a limit is, that helps me work out that this graph here actually has an asymptote at y equals 0. And if we're sketching graphs, we need to include the asymptote. So that asymptote should be drawn on there. Okay, that's the end.